All right, let's dive into some really cool research that's basically writing the recipe for the next generation of power. We're talking about a huge leap forward for the batteries that run, well, everything, from our phones to our cars. And it all starts with a problem I think you'll recognize.
Yeah, we've all been there, right? You're staring at that dreaded low battery icon, already planning your life around the nearest power outlet. These limits we deal with every single day, they all come down to the chemistry inside our current batteries. But what if there was something just dramatically better on the horizon?
Meet lithium metal. For battery researchers, this stuff is pretty much the holy grail. See, the graphite in the batteries we use today holds about 370 milliamp hours per gram. Lithium metal, it just blows that out of the water with over 3,800. That's not a small improvement, folks. That is a potential 10 times increase in energy density.
And look, this isn't some pie-in-the-sky idea. As the researchers point out, this is a major focus in the industry right now. The promise is absolutely enormous, but as with all these game-changing breakthroughs, there's always a massive catch, and this one has held the technology back for decades.
So here it is. Here's the big problem we have to solve. For all its power, lithium metal is also incredibly reactive. You could almost say it's fragile. It has this one corrosive weakness that makes it a nightmare to work with.
The second you expose pure lithium metal to normal everyday air, it starts to corrode. Instantly. It reacts with moisture, it reacts with nitrogen, and it forms this nasty, contaminated layer right on its surface. And this isn't just about looks. That layer completely wrecks the battery's performance and can even make it unsafe.
And you can see just how fast this happens. I mean, look, at minute 0, you have this perfect, clean, silver-white surface. A few hours later, it's already covered in this dark, cruddy layer. And after just one day, the metal is completely white and fractured with these performance-killing cracks. So the billion-dollar question is, how on earth do you manufacture with something this sensitive?
Okay, so that brings us to the big manufacturing hurdle. If you want to use a really advanced tool, like a laser, to shape this stuff, you have to have a perfectly controlled environment. You basically need to build a miniature cleanroom in a box.
Lasers are honestly the perfect tool for this job. They're incredibly precise, they're super fast, and because they're contactless, they don't add any new contamination. But even this amazing technology is totally useless if the lithium gets exposed to air while you're working on it.
So the researchers came up with a really clever solution. They built this custom, low-humidity chamber. Think of it as a little portable safe house for lithium. First, they packed it with 2 types of silica gel to just suck every last bit of moisture out of the air. Then, they designed it to be totally airtight. And this is the key part. They installed a special glass window that lets the laser beam in but keeps the bad air out. So, did it work? Oh yeah, it worked beautifully. Their goal was to get the dew point, which is just a way to measure dryness, down to minus 15 degrees Celsius. Well, their little chamber didn't just meet that goal, it smashed it, getting all the way down to nearly minus 24 degrees. This was the proof. They could create the perfect, clean environment to finally work with lithium. But building the box, well, that was just step 1. Now they had the perfect workshop. The next step was to figure out the exact recipe for using the laser on the lithium inside the box. They had to dial in the settings to get a clean, efficient process.
The key term here is something called the ablation threshold. The easiest way to think about it is like a power dial. You need to find the absolute minimum amount of energy to cleanly carve away the material. If you go too low, nothing happens. If you go too high, you just make a melted mess. Finding that perfect sweet spot is everything.
And while they were hunting for that threshold, they confirmed this really interesting phenomenon called the incubation effect. Get this, it turns out it's actually easier to process the lithium if you hit it with a bunch of rapid lower energy pulses instead of one big blast. It's like each little pulse softens up the material, making it easier for the next one to do its job.
So what does that softening up actually look like in numbers? Well, the researchers calculated what's called an incubation coefficient. Now, the math is pretty complex, but what this number does is give engineers a precise formula. It tells them exactly how much less power they need for every extra laser pulse they use. It turns a weird effect into a predictable, efficient manufacturing process. And you can see it right here in the data. With 200 laser shots, it took a certain amount of energy, over 10 microjoules, to even make a dent. But when they doubled the number of shots to 400, that incubation effect kicked in. Suddenly, they could create a crater using less energy than before.
It's a perfect example of working smarter, not harder.
Okay, so why does all this painstaking, detailed lab work actually matter in the real world? Let's talk about the payoff. This isn't just about one cool experiment. This is about creating the foundational recipe for the future of batteries.
What this research really gives us is a complete toolkit, a whole playbook. We have a proven design for the processing chamber, we have the exact data on how the laser behaves going through that window, and, most importantly, we have the precise power settings and that magic incubation number that tells us how to do it efficiently. This is the detailed recipe that other engineers can now grab and run with.
And here's the bottom line. This work is what could finally unlock mass production. It takes lithium metal from being this tricky, delicate lab material and turns it into something that we can actually manufacture reliably at high speeds. This, right here, is how a revolution in battery technology gets started.
And that brings us right back to the beginning, to the big picture. All of this research is a critical step towards a world with batteries that could last 10 times longer. So the final question is for you. What will you power when that happens? What new inventions, what new possibilities open up? It's a pretty exciting future to think about.